Welcome to another lesson in the Designing VMware Infrastructure video training series. In this lesson, we'll be discussing creating a logical network design. In this lesson, we'll start out by discussing how we go about defining a logical network design and what some of the components of a logical network design are. From there, we'll move into a discussion of how we go about deriving the logical network design. How do we arrive at the logical network design, and what are the factors that contribute to that logical network design? The next two sections will cover how we go about describing the virtual and physical network topologies that comprise the logical network design, and we'll wrap up this discussion of the logical network design with an examination of related areas. This is part of our ongoing effort throughout this video training series of making sure we maintain a holistic view of the design and take the time to examine relationships and dependencies between components of the design so that we can ensure we understand design impact and the effect of changing certain areas of the design and what effect that'll have on other areas of the design. When we talk about defining a logical network design, what is that logical design going to include? As you've heard in other lessons in this series, the logical design again is a high-level design, and it's not intended to be detailed with specifics and configurations and that sort of thing. And we'll follow that same path here when we talk about a logical network design. We're going to include both a virtual network topology and a physical network topology in the logical design. We will get a bit more detailed here, as you'll see in some examples I'll share with you later on in this lesson, but we're not going to be mapping these onto specific topologies in most cases. Now, you do see listed here that a physical network topology is part of this logical design, and at first glance you might say, wait, hold on, we're talking about logical design, not physical design, so why are we talking physical network topology? Well, even though we're talking about a physical network topology, this is still part of the logical design. What we're referring to here is the logical view of the physical or real network topology. We haven't mapped it onto actual products or solutions yet. That's something we will do during the physical design process later on. We are going to talk about a logical representation or a logical view of the physical network topology as part of this process. With an idea of what makes up the logical network design, let's now take a few minutes to talk about how we go about deriving the logical network design. Recall from another lesson in this course, the Determining the Design Factors section in this course, we talked about the design factors that contribute to every VMware vSphere design, those design factors being requirements, risks, assumptions, and constraints. And of course, these factors are going to continue to influence the logical network design much in the same way that they influence the logical compute design, a logical storage design, logical security design, or a logical management design. Specifically, as we look at the information that was gathered during the information gathering process, that was used during the requirements analysis to create the requirements, both functional and non-functional, and how we derived the rest of the design factors from those requirements, some specific pieces of information or specific factors that are going to influence the logical design include things like network utilization. How heavily utilized is the network? Are we seeing lots of traffic, or is the network pretty lightly utilized? In a lot of cases, you see networks that are lightly utilized. In most cases, with a few outliers, this is pretty common. What are some of the security mandates? Security in particular often has a significant impact on the logical network design because it may mandate certain requirements for how network connectivity is handled. What are some of the operational requirements? For example, are we bound by requirements, or is our design going to be influenced by requirements that specify that the network group must have end-to-end control over the network? Are there other operational requirements? Do we have to have the ability to have a per port ACL, or do we need to have support for LLDP inside the networking design? These are all things that will influence the logical network design. Finally, are there technology constraints? Is the design constrained in some way by saying that we have to use a specific technology or a specific product, perhaps to observe budget requirements, or because this is what the organization or customer is most familiar with? Information on all these factors is information that you should have gathered during the information gathering phase that we described in another lesson in this course, and would therefore be put into the design factors, those four key things that influence the vSphere design. Let's take a look at an example of a potential requirement that would have a direct impact on the logical network design. Here we have a functional requirement that says the design must support applications and workloads running in physically segregated network security zones. Now, this is a functional requirement because it does say that the design has to have a certain function. It doesn't say how we go about supporting that, which you might see in a non-functional requirement or a constraint. In this case, it's saying we have to be able to do something. We have to be able to support applications and workloads running in physically segregated network security zones. Now, what sort of impact does this have on a logical network design? Well, we're going to talk about that as we look at some examples of logical network designs in just a few moments. But first, I want to talk about some of the specific components or sections or pieces of information that you will use to describe the topologies that represent your logical network design. First, we'll talk about how we go about describing the virtual network topology. There's a number of different components that you're going to use to describe the virtual network topology. Those components include whether or not you'll be using a standard vSwitch or a distributed vSwitch. And if you are going to use a distributed vSwitch, whether you will use the VMware distributed vSwitch or a third-party vSwitch, such as the Cisco Nexus 1000V or the IBM distributed virtual switch. How many virtual switches are there going to be? How many uplinks will the virtual switches use? And what will be the number and configuration of the different port groups and VM kernel ports on those virtual switches? All of these things will play together to help you describe and lay out what the virtual network topology is going to be. And that virtual network topology is a key part of the logical network design. With that in mind, let's take a look at a couple examples of some virtual network topologies, and we'll begin to explore some of the factors that might lead us to one design over another design. Here in this instance, I've got a simple diagram that shows a single ESXi host with two virtual switches, vSwitch 0 and vSwitch 1. We can assume that these are standard vSwitches, not distributed vSwitches. Each of these vSwitches has a pair of uplinks represented by the network card symbols there, and each of these uplinks connects to an upstream physical switch. So you can see here that we have some redundancy, which is obviously a desirable quality. We have redundancy at the NIC level, we have redundancy at the physical switch layer. So if there were a single point of failure, if there were a single failure here, we wouldn't lose all connectivity. This is one way of how you could divide up 4 NICs. And there's a lot of different ways we could do a virtual network topology. One of the strengths of the virtual networking functionality that you find in vSphere is that it can be easily reshaped. So we could use a design like the one you see here, where we have 4 uplinks, 2 virtual switches, that sort of thing. Or we could just as easily take this same design and reconfigure it a little bit to come up with this design. Here again, we have a single ESXi host, but instead of having 2 virtual switches here, we have 1 virtual switch, vSwitch 0. With 4 uplinks, and again the uplinks connect to physically separate upstream switches. Why would an architect choose one particular design over another design? Is it functional requirements? Well, of course it's functional requirements. It's going to be functional requirements. It's going to be constraints. It's going to be assumptions. It's going to be risks that are going to drive whether we go with 2 virtual switches or whether we go with 1 virtual switch. So as you prepare to create your virtual network topology, this idea of really being able to understand how the requirements apply against the design is going to be critical. With that in mind, let's take a look at a requirement, a functional requirement, that might influence which design you would choose to use. The requirement you see listed here says the environment will leverage iSCSI using the vSphere software initiator for shared storage access. So how does a requirement like that shape or influence a virtual network topology? Well, there's a number of different ways you could address that. You could continue to use 4 NICs. You could move to faster links. We haven't specified what the speed of the links are, so maybe these were 1 gigabit links and we're concerned about using software iSCSI with 1 gigabit links in addition to the virtual machine traffic, in addition to vMotion traffic, in addition to management traffic. And our concern would be founded or unfounded based on the knowledge that we have of how much network utilization there is. This is information that we got from examining or assessing the current virtualized environment. One way you could address a requirement that says we're going to leverage software iSCSI would be using a design similar to this one. So here in this case, instead of 4 uplinks, we have 6 uplinks, or 6 NICs altogether, and 3 virtual switches. And some of the virtual switches connect to one pair of physical switches, and the third virtual switch, vSwitch 2, actually connects to a separate set of switches. This is a not at all uncommon sort of design where you have IP storage traffic, iSCSI in this case, connecting to a physically separate network. This might also be a way that you would address the earlier requirement of saying that certain workloads were connected to physically segregated networks. There's a number of different ways you could do that. Note that we don't have to break our physically segregated network onto a separate vSwitch. We could change a failover order on a port group, which is why the port group configuration is a key part of your virtual network topology. But in this particular case, we have a scenario that would accommodate using software iSCSI. It would accommodate, if needed, the requirement to have physically segregated workloads, and again have redundancy. We have no single point of failure. We are addressing the functional requirements as we understand them so far. Now, this is not the only way you could go about doing that. There's a lot of different ways we could combine these different pieces together, but the key as the architect in understanding which way we should combine them together is this whole idea of understanding the impact of the various design decisions. If I choose to combine these from 3 virtual switches to 2 virtual switches, what will the impact of that design decision be? How will it affect the rest of the design? What does the number of virtual switches impact? What does the number of uplinks impact? What does the configuration of the port groups impact? How does it affect the rest of the design? This is the purpose behind the sections that we include in the different lessons in the video training series that help us examine how these relationships look at each other. We'll do that for the networking side of the house here in just a moment. But now let's switch gears from the virtual network topology and talk a little bit about the physical network topology. Recall earlier in this lesson that I said that even though we're talking about a physical network topology, we're not talking about the physical design of the network. Here we're talking about the logical view of the physical design. And so here we're going to be providing a logical representation or a logical description of the number of physical switches that are going to be used. Much as you saw in the previous diagrams, we just have to say this is how many upstream switches we're going to use to satisfy the redundancy requirements or the bandwidth requirements or the traffic segregation requirements. What is going to be the configuration of link aggregation? Are you going to use link aggregation? If so, how will it be configured? And finally, what is the link speed going to be? Are you going to be using 1 gigabit links? Are you going to be using 10 gigabit links? Are you going to be using a combination of links? Because that will also affect your design. The physical network topology, as you can see, isn't quite as detailed or as in-depth as the virtual network topology, but both are important parts of the logical network design that you need to create at this point in your design process. From here, let's move into examining the relationships and dependencies between these different pieces as we prepare to wrap up this lesson. Here's another mind map that talks about a logical network design and the different components of the logical network design and the different areas that each of these components or sections affects. So when we talk about changes to our physical network topology, such as including more physical switches or the type of physical switches, we can see that there are different areas that are affected. The physical network topology, for example, will affect what kinds of network equipment you're going to use. It's going to affect your virtual network topology because these two are inextricably linked together. You're going to have to abide by financial constraints, so you can't just go out and buy as many physical switches as you want or whatever model that you want, but you have to abide within the budgetary constraints that are in place. It can have impacts on your compute and storage designs. For example, if you are looking at IP-based storage, then your physical network topology is obviously going to have a direct impact on your IP-based storage design. There are power environmental constraints and security requirements that will also come into play. Similarly, when we start discussing the virtual network topology, we can see some of the dependencies or relationships include effects on licensing, on the management design, on financial constraints, operational considerations, the physical network topology, and security requirements. And finally, network speed is going to affect both the physical and virtual network topology, as well as some financial constraints and operational processes or procedures. Now, one of the very cool things in my mind about using a mind map is that we can drill in on one particular piece. So here we're talking about a logical network design, and then we have branches off of that for physical topology, virtual topology, that sort of thing, and then we branch off from there. But what if we were to center in on a discussion of the virtual network topology and then drive into the components that make up that and what those will affect? What might that look like? If we were to take virtual network topology and make it the center of our diagram here, then we can begin to branch off the virtual network topology and say, well, what are some of the decisions that go into play in creating the virtual network topology? Well, we talked about some of these earlier in this lesson. We talked about using a standard virtual switch versus a distributed virtual switch. What are the impact going to be of choosing one versus the other? Obviously, we have to do the right thing to meet the functional requirements, because if we can't meet the functional requirements, then the design is not going to do what we want it to do or what the customer wants it to do. It's going to have an impact on licensing. Are you appropriately licensed to use a distributed virtual switch? And it's going to have an impact on your physical network topology as well. Just like the number of uplinks, which is another key component of the virtual network topology, will have an impact on your physical network topology, or the level of redundancy you can offer. And finally, the number and configuration of port groups was something that we mentioned, because this affects redundancy, this affects operational considerations, this affects your network topology, and it affects how you go about satisfying functional and non-functional requirements that are defined by you early in the design process. Now, if we go through this iterative process once more and we say, okay, we started out with a discussion of the logical network design. We then drilled into a node on virtual network topology. Now, what if we drilled down one more level and said, let's focus in on the number and configuration of the port groups. What is that going to look like, and what kind of impacts will that have in other areas? Let's look at that real quick. So as we drill down one more level again in our use of a mind map type diagram to examine relationships and dependencies, we see we'll center in now on the number and configuration of the port groups, which is a portion of the virtual network topology, which in turn is a part of the overall logical network design. What are some of the design decisions that go into the number and the configuration of the port groups? Well, this would include things like the NIC teaming policy. Are you using the default NIC teaming policy, or are you going to switch it to something else? That, of course, would be affected by your decision of virtual switch or distributed virtual switch, as some NIC teaming policies like load-based teaming are available only on the distributed virtual switch. But it'll also have an effect on other areas. It'll affect your network design, because if you choose to use a link aggregation policy, such as route based on IP hash, then there has to be an appropriate configuration on the physical side to support that configuration. On the other hand, if you were to go with a default route based on originating virtual port ID, there would not need to be a corresponding physical configuration. We have an effect on redundancy, an effect on the network equipment we're going to use, an effect on the operations, because how I go about troubleshooting one teaming policy configuration may be very, very different than how I go about troubleshooting a different teaming policy. As we continue looking at the number and the configuration of the port groups and the components that make that up, we have to decide, are we talking about a VM network port group or a VM kernel port group? These obviously are going to have an impact on connectivity and how we go about establishing connectivity to either the virtual machines or the VM kernel itself. What kind of security configuration will be included, and what kind of impact does that have? It could impact compliance, it could impact your functional requirements, and even your non-functional requirements or your constraints. Finally, what about things like uplinks or failover selection? Are you going to limit the port group to be able to only use certain uplinks off the virtual switch, or to preferentially prefer some uplinks over other uplinks? That's going to have an effect on redundancy. It'll have an effect on the failure scenarios, so you're going to have to incorporate different failure scenarios in your testing to ensure that you haven't overlooked a potential failure scenario that might cause an outage. It will also have an effect on operational considerations as well. Now, we could continue to drill down, so we could, for example, go into uplinks failover selection and drill down again and look at the specific settings in there and begin to explore the relationships and dependencies. But I think you get the idea of how you can use a tool like a mind map to map out or understand the relationships and the components, and then drill down consecutive levels till you get as deep as you need to go to understand the impact of a particular design decision on other areas of the design. As we wrap up this lesson on the logical network design now, let's review what we covered. We talked about defining the logical network design and what the components are that are included in a logical network design, the physical network topology, or a logical view of the physical network topology, as well as the virtual network topology are both included. We discussed the factors that are going to affect the logical network design and how you go about using those design factors, the risks, the assumptions, the constraints, and the requirements, both functional and non-functional, to affect the design, how they play into causing the design to be a certain way, and how they drive the architect to choose one particular design over another design to find the right design that best fits the requirements. We discussed describing the virtual network topology as well as the physical network topology and what specific pieces of information are going to be included when you describe those topologies as part of the logical network design. And finally, we wrapped up this section with an examination of our related areas using a mind mapping tool, as we introduced another lesson in this course, to help explore relationships and dependencies on different areas so that we'd have a better idea of design impact. If we change one thing in one area, what are the related areas that are going to be affected by that, and what will the effect be? That's it for this lesson in the Designing VMware video training series. Thanks for watching.